Hi guys, welcome back to another episode of Introduction to Computer Networks. This is Polly speaking live again from National Taiwan University. And hi Eslam, hi Cheng-En, Han Zhen. Okay. Today the lecture is going to be straightforward. Okay. We'll start talking about congestion control. Recall last week there was a take-home quiz, right? I asked you guys to pretend to be a Uber driver, and you discover that there's congestion on the highway. I ask how you communicate the situation to your friends who are also Uber drivers so that they can avoid coming on the same route, right? And hey, some of you are very creative, but generally we discover two solutions, right? One is that many of you say that, hey, why don't I just text, the friends, right? Form like a line group or a WhatsApp group so that you can just text and everybody on the fleet will see. Okay, so you transmit a message from within the traffic, okay? And many of you say, hey, just ask all these other Uber drivers to watch or to, use Google Map. Because on the Google Map, you see somehow there's congestion, right? So that is actually asking the Uber drivers, to try to discover if there is a congestion from where they are, from where the source of the congestion might be created. All right, so you see there are two flavors. Congestion control, notification from within the network versus having the ends to discover there's a congestion. So that's what we want to talk about. But let me say hi to the rest of you. Jun Huan, Ming Huang, Ting Xuan, Lucas, Ali. Okay, welcome back. And you know what, guys? If you are in today, you are in for a treat. Okay, because let me just finish the reminders. The assignments this week, we do have PA7. For PA7, you'll be learning a new set of APIs, okay? And the goal is to try to implement a web server in the end from PA7, 8 to 9, and a secure web server in the end. But PA7 is like the first step, a baby step. It's relatively straightforward. You guys should not have any problem, okay? So no worries. This week, however, we have quite a few quizzes, okay? There are actually 5 of them. This is probably record high, okay, within a week. Not to mention that next Wednesday is exam number 2. So in a way, the load this week is a little bit high, okay? But for exam number 2, the scope is chapter 3 and 2.6, the multimedia networking part of chapter 2. So it's somewhat contained, okay? It's not as wide as exam 1, okay? And there are not as many things that you need to memorize. Good. And yeah, hi Yuting and Eneko. Good. So topics today, straightforward as I mentioned. We'll talk about congestion control. And the first 2 videos are to talk about the 2 flavors of congestion control. One is to do it end-to-end. The other is to do it in the network. Okay, so pay attention to these 2 videos because at the end of it, Polly is going to take a poll and ask which one you prefer. So the first one is the congestion control, but end-to-end approach. With the scenarios elaborated, you see, particularly in scenario 3, the only solution or the only effective solution to a congestion is to what? Just slow down. And therefore, the 2 key design elements in a congestion control mechanisms are these. First, detecting when a congestion is occurring. Second, notifying the traffic sources that's causing the congestion to slow down. And there are 2 major approaches allowing us to achieve those. First is called the end-to-end based approach, the other, the network-assisted approach. Now, from the name of it, you probably guessed. Yeah, end-to-end meant the end systems are doing much of the work, detecting congestion, informing the traffic source to slow down. Network assisted, on the other hand, is asking the routers to do all these work instead. Let's first focus on the end-to-end approach. So in this approach, the end systems will need to infer if there's a congestion occurring inside the network. If you recall back in TCP, okay, what we're doing is sending multiple packets in one flight to the receiver. Receiver sending ACK back. And all these packets and ACKs carry the sequence numbers. So receiver can actually detect a gap, okay, in the packets being received, and therefore sends duplicate ACKs instead of new ACKs. So receiving duplicate ACKs is a way of detecting if there's a loss, or the sender side can simply time out and then retransmit. That's also a signal of detecting there's potentially a congestion inside the network. So that is, observing from the loss occurring, inferring there's a congestion. One can also observe if there's delay changes. Okay, so for example, when we send packet out, let's track the sending time. Okay, let's track also the time when the ACK for that packet comes back. Calculate the difference, you get the round trip time. And if you observe for a long enough time, you might see, oh, the round trip time is increasing. When it goes beyond a certain threshold, then you could say that, also, network is running into a slight congestion there. Okay, so overall, general mechanisms, observe packet losses. If there is an increasing trend, observe the delay. If there is an increasing trend, then you're going into this hotter zone where congestion is likely occurring. Now, taking this approach, we do not get explicit feedback from the internet, from the routers inside the internet. And taking the end-to-end approach, we'll have to also guess or infer the right sending rate. Okay, so this is for the source to know exactly what is the right rate to send the data so that we do not overwhelm the network in the meantime, not being too conservative, too slow sending the data out. Okay. And this is actually rather hard to do for the end systems. After all, they're actually at the very edge of the network. The congestion could be happening anywhere inside the network along the path. So what the end-to-end approach is doing is this, okay, guessing. By trying a certain rate and observe if there's a loss, okay, if there's a growing delay. If not, then cool. This is actually within the available bandwidth. So maybe let's raise the rate a little bit and see, right, if there's a loss now, if the delay increases now. If not, then hey, we're still safe. Let's, increase it so that we're not too conservative, too slow sending the data out. Now, but if we exceed a certain point, and as a result, we begin to see loss, and we begin to see the delay increasing drastically. Yeah, that is actually not good. That indicates that we're probably exceeding the available bandwidth threshold, and therefore we are sending data too much, too fast into the network. So if we are failing, if we are detecting these signals of congestions, then that's slowdown. Okay, so end system here to infer, to find out what is the right sending rate is by trying. Okay, pushing. If we over push it, let's come down again and then try to push it again. Well, if not good enough, slow down again. So this is in fact the approach also taken by TCP. This is actually very natural because TCP being a transport layer protocol, it's actually implemented receiving side, sending side both at the end systems. Therefore, it implements an end-to-end based congestion control mechanism. Yeah, so you can see that it will work. In fact, TCP takes the end-to-end approach. But you see also that in order for the end-to-end approach to work, we need to wait for these feedback from the network by checking whether there's loss, by checking whether delay are suddenly increasing. And hey, if you recall in TCP, how do you discover a packet loss? You might need to wait, right, for this timeout interval. So yes, you're right. Taking this end-to-end approach, to react to the congestion, it might be a little bit slow. Second, you are also guessing what is the right transmission rate by trying more and wait until if it's too much or not enough. Okay, so the precision of determining the transmission rate is also not that high. Therefore, it might also take some time for this end-to-end approach congestion control mechanism to discover what is the right transmission rate. Okay, so even though it does not require the router, which is a network layer device, okay, and TCP or in the transport layer, we are in the transport layer. Okay, so This end-to-end approach does not require cross-layer communication much, simple, but time to discover condition and time it takes to react to condition, okay, both will be long. Now, the second approach, end-to-end, you guessed, discover fast, reaction fast, but complicated because somehow router need to communicate something to the transport layer. The network-assisted approach. Okay, so in this approach, routers will be doing the condition detection. But how? Well, we also need to observe something, but this time we could actually observe something that's very directly related to condition. This, the queue size. Okay, so this is the queue of these packets gathering at the entry point of the router. Okay, so condition is this: sources of the traffic sending data too much, too fast into the network. Inside the network, we have these routers, right, handling packet forwarding. If the outgoing rate is slow and incoming rate is high, then these packets will need to what? Be buffered temporarily, okay, at the entry point of these routers. And therefore, they get a chance to wait for their turn to go out on the outgoing link. If the outgoing rate is slow, incoming rate is high, queue gets long, and free buffer space gets small, right? So queue size or free buffer space, okay, changes of these, okay, are good indications of a condition occurring. Now, routers, however, are the devices in the middle, okay? How do the routers inform the sources so that the sources know that they need to serve them? Yeah, this is the way it's done. Okay, so there are these bits, special bits, okay, inside the packets. So when these packets travel through a router and the router is so busy, queue size is so big, or free buffer space is so small, these bits get turned on. And when the packets arriving at the receiver, receivers can check these flags or check these bits and then inform the source of the data, the sources of the packets. Okay. Now, in internet, okay, the TCP/IP protocol suite, okay, yeah, let me explain. Yeah, TCP is actually a transport layer service, okay, but sometimes we also call the transport layer the TCP layer. IP is actually a network layer protocol. And therefore, sometimes we actually refer to the network layer as the IP layer. So TCP/IP here is actually referring to the internet protocol stack because the transport layer is running TCP. The network layer is running IP. So these two are the very typical classical protocols that are running, okay, supporting the operation of the internet. So in TCP/IP or in internet, we have these special bits and we call them the explicit condition notification bits. So when the router inside the internet, the queue size gets large enough or the free buffer space gets small enough, we set the ECN bits on. And therefore the receiving end, the TCP receiver there, seeing the ECN bits on can inform the source to send them. Now that is how the routers in network-assisted approach detect condition and notifying the source of the condition. What's nice about this approach is this. The routers there observe exactly how much free space there is, okay? And dividing by the number of flows that's going through, number of connections that's going through. Hey, routers can also be more explicit, telling the receiver to inform the source. Now, set the sending rate to this size. Set your sending window size to a particular size, such that we will not be overwhelming, the router buffer space. Just like the flow control mechanism, right? Receiver there observing the receiving buffer. Depending on how much is free, set the sending window size accordingly, and voila, problem solved. Receiving buffer will never be overwhelmed. Similarly, the router's receiving buffer here will never be overwhelmed. All right, so towards the end of this chapter, you will hear exactly how the ECN bits work. Okay, so there's actually a version of TCP that implements the network-assisted approach. Now, the pop poll here. Between end-to-end and network-assisted approach to do condition control, which one do you like better? Oh, I see. Yujie. Oh, okay. There are more of you preferring network-assisted approach. Okay, let's see. Oh, ouch. Okay, LA representation, finally. Oh. But you know what? LA representation, TCP is on your side. TCP is on your side. All right. Yeah. I think Ryan elaborated a little bit more because network assisted, it seems more precise. Right? You know exactly there is a congestion, and a notification comes right away, and you notice the congestion immediately. I know, guys. Yeah, but TCP is definitely suboptimal in discovering congestion and try to recover congestion. Okay, and you will see from quiz 27. So before we start talking about how TCP does congestion control in this end-to-end way, we'll go through quiz 27, and you will see. Okay, this again. Okay, let me go to. Okay, so this is quiz 27. So this one is very similar to the traffic problem, traffic quiz we had last week, as well as the Lord of the Ring quiz. Okay, so I'm actually asking you to brainstorm, okay, about a problem of the same nature, okay, and see if we could come up with solutions ourselves before we take a look at how internet addresses these problems. Okay, so similarly, this quiz, okay, is going to ask you guys to brainstorm or solve a problem. That is to discover what is the right price for merchandise. All right. So quiz is called The Price is Right, and this is one of Polly's favorite TV game shows. Okay. And so the way the game show works is there are two stages. Okay. In the first stage, a number of these members in the audience will be invited, and they'll be estimating the price of a merchandise item. Okay? And the team with the closest guess, but not exceeding the price, wins and enter the second stage. In the second stage, okay, there's just one contestant. Within 30 seconds of time, the contestant will be presented another merchandise, usually fancier. Okay, and the contestant will keep guessing what is the right price until he or she gets the price right. Okay, and Polly, as the game show host, will try to provide feedback. When your guess is too low or lower than the exact price, I would say too low. When it's too high, I say too high. And you adjust your guess until it's precisely right. Okay, so let's go to the Discord space. Guys, are you ready? Good. Hey, wait. Hey, guys, welcome back to The Price is Right. Okay, this is your game show host, Polly. Okay, today we are gonna have 16 contestants, okay, competing for stage 1. Guys, okay, in stage 1, within this setting, there's no need to log into the Google Meet session. All right. Polly is going to post the merchandise on the channel. Each of you guys will have 1 minute to discuss, okay? Discuss with your teammates, okay? And one of you, one for each team, okay, will type the team number and your estimate. No editing after the estimate, but you can post, okay, another. If you really regret and you need to change that, you will need to post later. Okay, you can delete that estimate and post it later so that we know which estimate comes earlier, which one comes later. Okay, and you have only 1 minute time, so you need to do that within a minute because after that, Polly is going to post the true price. All right. And just in case 2 or more of the teams are the closest and below the actual price, okay. So meaning, for example, you guess the same price, okay? Then we'll take the earlier post as the winner, okay? So this is stage 1. The winner of stage 1 will enter the stage 2. Okay, I see. You guys are ready. Oh, by the way, all these items, I'm asking the NT dollar price, okay? So, hey, international students, have your calculator ready so you could do the conversion. In stage 2, The winner, then we'll need to mute the TV stream, the YouTube stream. Okay, this is to avoid echo because you are gonna join the Google Meet session here and interact with Polly directly. All right. Similarly, a merchandise will be posted on the channel. Okay, and I'll give you a few seconds to breathe and count down, and then we'll begin. You have 30 seconds. Within the 30 seconds, you would continue to guess what is the right price until it's right. Okay, and Polly is just gonna give you feedback: too high, too low. All right, until the time is up. All right, so let's see. Shall we start? Okay. Yeah, let's put out the first item. And guys, okay, dear contestants, the first item is a condenser microphone. Yeah, this is almost a necessity these days if you go online. For example, playing games, streaming, or taking an online course. So yeah, this is a very popular item, obviously, because it's Amazon's choice. All right, guys, gather your teammates and discuss. You have 1 minute. Okay, as soon as you know what is the right price, just type it up on the channel. All right, there. Polly is starting counting time. Wow, 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 wow. All right, time's up. Guys, you guys all overestimated the price. Guys, you guys all overestimated the price. We'll have to do this again because there will be no winner. Yeah, I know, it's absurd. Someone actually makes condenser microphone this cheap. Okay, so let me see. Most of you guessed something like in between 1,500 to 2,000. But you know what? Let me see. The lowest price we had earlier is $849. Even this is higher than the true price. So guys, we need to do this again. All right, so you guys get 30 more seconds. Okay, within 30 seconds, type up your new guess. Okay. Lower than 849. Okay, then. 499, 250, 300, 830, 500, 450, 500, 680. All right, time's up. Okay, I see there are still some of you typing. Hurry, hurry, hurry. Hurry, hurry, hurry. Okay, the moment of truth. Oh, two more teams typing. Hurry. And Nicole, still typing? Okay. Hey. Ta-da! Yeah, the price is 805. Right? Bargain, isn't it? Therefore, it is Amazon's choice. So let's see. Well, who's the winner? You know what? Team 1, 800. This is really close. Let's see if there's any guess between 200 and 205. Yuan Hao, you are very close. Qingying, you too. Oh, sorry, Team A. You are just slightly above. You know what? It looks like we have a winner. Okay, and the winner is Team 1. All right, Team 1. Okay, please do what you need to do. All right, and that is first mute the YouTube stream and join me at this link, the Google Meet session. Okay, let me unmute myself. So code, I think Yuji and Ryan, one of you will need to join me in the Google Meet. It's okay to turn off your camera because this is gonna go public. Yeah, so if you are a little bit shy, only your voice needs to show, but not necessarily your video. Okay. Okay, let's wait for Ryan or Yuji to join us. Okay. All right. All right. Congrats already, Ryan.
Thank you. Can you hear me?
Yes, I can hear you fine.
Okay.
So now let's bring up the merchandise. You'll be guessing what the price is. Wait a second. I need to scroll all the way down. Yeah. So this is the item you'll be guessing the price for. It's a dual screen mobile monitor. All right. It's a 15.6 inch wide QLED, high quality, high resolution, really lightweight and thin. All right. Ryan, are you ready?
Sure.
Okay, so I have a timer here. When I say let's go, I'll let the timer run. And when it expires, it's gonna ring, all right? And during this period, before now and ringing, guess the price of the item. Good? Now, let's go.
6,500.
Too low.
9,000.
Too low.
1.5K.
Too high.
1.2K.
Too low.
1.4K. 1.35K. 1350.
1350 too high.
1250.
Okay, time's up. 12. Oh, there. 12. Say tell the last guess again.
1250.
12.
Oh wait, I mean not. Okay.
12. Do you mean 12,500?
Oh yeah. Yeah, that's my bad.
Okay, it's still a little bit low.
Okay.
Okay. Now, how about I give you 10 more seconds? Now you know it's between 12,500 and I think 13 something. Okay, so you have how about 20 seconds? Okay, I can feel that you are really nervous. Okay, Ryan, take it easy. Take it easy. Okay, we're here to give things away. All right, so in this particular case, the extra participation points away. So 20 minutes in between 12,500 and 13,000. Let's go.
Okay. 12,750.
Too low.
12,850.
Too high.
12,800.
Too high.
12,775.
Too low.
12,785. Okay.
Hey, we have a winner. 12,785. Congratulations. All right.
Oh.
I guess the 20 seconds helped. Okay. Hey. To make sure that this game show is credible, let me show the prize. Okay. It is 12,850. Sorry,
Oh.
785. Oh wait, did you get
I think I did say that.
Yeah,
Yeah,
you did say this, right?
12,007.
Right,
Yeah.
right, great. Congrats. All right, thank you, Ryan, for participating. Okay, you, Yuji, and August will all receive 20 extra participation points.
Yeah.
Yay! Hey, class, congrats them. And you know what, guys? That's how about we play it again? Ryan, I'm gonna hang. Please exit the room. Let's try to play it again. Guys. Hey, learn from what Ryan did. Remember? Hey, after Polly say 12,500 and 13,000, what did Ryan say? 12,750. What is that? That is binary search, isn't it? Yeah. All right. So let's do it again. So guys, you guys have another chance. So let me post. Let's go back to stage one. Let me post an item for you guys to participate. So team one, you are now disqualified because you guys have already 20 points extra. So let me put this up. Okay, great. And you know what? This is something really convenient coming since the summer is coming up. It's a cordless fan, okay? That is tiny, mobile, and it works also as a power bank, okay? So this one is, I think, close to Amazon's choice as well, okay? And it comes also with the remote control, okay? Really nice with a clean design. Now, you guys have 1 minute, okay? Discuss with the teammates and type up your guess, okay? So let's begin. $4. All right, time's up. Okay, are we done? Okay, I think we're done. Okay, Yujie is typing. All right. Okay, that's all. Guys, you guys have a much better sense this time, I have to say. But you see nowadays, the prices are all kind of, the prices can skip. Where's my cursor? Oh no. I can't believe my mouse. Okay, it just died on me. Oopsie. Ouch. Sorry guys, give me a couple seconds. I need to change the battery of this thing. Okay, almost there. Let's see. Still not working. So maybe it's just that my mouse is dead. All right. I do have a backup. There we go. Okay, I'm back. And the real price for the fan is, okay, ta-da, 1424. 1424. Let's see who the winner is. Okay, so far team A is the closest. 1424. 1424. One, 4, 2, 4. Still teammate. Oh, okay. You know what? The winner is Team 12. And on the first guess and the earliest guess. Okay. Well done, Team 12. Okay, now, Team 12, you need to send someone to join me here at the Google Meet session. Okay, mute your YouTube stream. Yeah, let's wait for Team 12. Just a little bit. Okay, looks like Pinxiang.
Oh, hi. Can
Hi.
my voice?
Yes, I can hear you perfectly fine. Guys, can you hear Pinxiang? Pinxiang, can you speak?
Yeah.
Yeah, I think they can hear you fine. Okay, good.
Okay.
And you know what? Yes, they hear you. All right, great. Let's see. I haven't had any semester that I need to give out 40 participation points. Let's see. Okay. So here's the merchandise. And it's a fancy Sony Bravia 4K high definition TV. All right. So this is top of the line. Okay, huge screen. All right. So are you ready?
Yeah.
Okay. So why don't we do 30 seconds first and see? Okay.
Okay.
Good. And guys, now you know the tip is why don't you just read the numbers instead of saying how many thousand, how many hundred. Okay, skip the thousands and hundreds. That might help. All right. So let's begin.
50,000.
50,000, too high,
30.
too low,
35.
too low.
37.
Huh? 40 is already too low.
43.
40, 43,
43.
too low,
45.
too low,
47.
too low.
Uh,
All right, all right, all right, all right. You get 20 more seconds. You know it's now between 47 and 50, right?
yeah.
47 and 50. 20 more seconds.
48.5.
Too low,
49.
too low,
49.5.
too high,
49.25.
too high,
49.50. 15.
too high.
49.05.
Oh, you just a little bit too high. Just a little.
49.03.
That's right. Yeah, just a little bit over time. But you know what? Why don't I do it this way? Okay, I cannot give you 20 points, right? Because it's still not within time. But you are so close. How about 15 participation points? Okay, good. Guys, ooh, well done. Hey, these guys are good. Yeah, this is the first year I need to give 35 participation points. Okay, and the true price 49,003. Oh, wait. Did I get? Yeah, 49,003. Okay, good. Great. So, guys, if you have observed, yeah, if I say too high, drop. If I say too low, raise the price. Similarly, that is also what TCP does. Okay, when there's packet loss, drop the window size. When the packets are received, eggs are coming back, increase the window size. All right. So the next two video is to explain how TCP increases and decreases the window size. Okay, somewhat similar to what you guys are doing. Sometimes, hey, doing the binary cut, but sometimes do more incremental increase. So this is what AIMD is doing. And we'll take a look at an example of an end-to-end based approach, TCP's condition control mechanism. And TCP does it this way. The sender will increase the sending rate gradually if there are no packet losses detected. But as soon as there's a packet loss, we drop the sending rate drastically. So point number one here, packet loss is used as an indication of network congestion in TCP. Point number two, TCP is actually implementing a trying, failing process to discover what is the proper sending rate. Now, by sending rate here, I'm adjusting. In TCP, it's implemented this way by changing the sending window size. You see that the sending window size is a limiting number of bytes we can send out within one round trip time. Therefore, increasing the sending window size is increasing the sending rate. All right, the exact process of doing the trying and failing is called the additive increase multiplicative decrease, or AIMD to be short. So AI describes the increasing process of the sending rate. So this is done by setting the window size and such that it increase one packet per round trip time. And the decreasing part is this cutting the window size to half of it, okay, after detecting a packet loss. So you see the increasing part is slow and linear. The decreasing part is drastic, multiplicative. So additive increase, multiplicative decrease. Okay, linear increase, multiplicative decrease. So if I show the sending window here over time, we'll see when there are no losses, the window size is going to grow linearly. As soon as we hit the loss, we drop the window size drastically to half of it. So additive increase, multiplicative decrease. So each of these AIMD episodes looks like a sawtooth. And that is why people often say TCP's window size change over time shows a sawtooth behavior. One thing I want to add is this. We say we increase the window size by 1 packet per round trip time, but TCP sequence size is counting data by bytes. Window size is therefore also counting the maximum amount of data we could send out by bytes. So what do we mean by increasing the window size by 1 packet? That doesn't make sense. How do we implement that? Yeah, so the fact in the implementation, what's being done is to increase the window size by 1 maximum segment size. Okay, so MSS here, if it's configured to be 1460 bytes, then the window size is incremented by 1460 if there's no loss detected within a RAM. And this is actually related to the second point I want to stress. Yeah, you see here, the full name of the sending window is no longer WND. Right? It's actually called the congestion window size, CWND. Because the sending window size is dynamic in TCP, and it's actually controlled by the congestion control mechanism. That's why the window is now referred to as the congestion window. And this is TCP's process of trying to probe and discover the available bandwidth. Now let's bring up the diagram we used to explain TCP. Now it's counting bytes. Now each of these is what? A byte. If we'll be generating a new packet, then we'll be using the byte stream number here as the sequence number of the new packet. Right? So what you're seeing here is I'm updating the diagram such that this term here is no longer WND, the sending window size. We are now calling it the congestion window size, okay, because this here, okay, CWND is dynamic. It can be large or small. It's no longer a fixed size. And how large it is depends on how the network is smooth. How small it is depends on how bad the network is congested. And the quantity CWND here limits the number of bytes there can be between the last byte sent to the last byte act. Last byte act. So green here are counting the bytes that have been sent and have been act. So the last byte act is the last screen. Yellow here are the packets sent or the bytes sent but not yet act. So last byte sent is here, the last yellow. Okay. So last yellow, okay, subtracting the number of the last screen. That means the number of yellows. Okay, so CWND here limits the number of yellow bytes there can be at best. Last, so we say TCP's congestion control is done by controlling the sending rate or changing the sending rate to discover what is the right one. Okay. We already mentioned earlier that is actually implemented by changing the window size, changing the congestion window size, because the sending rate is essentially the congestion window size divided by RTT, because within a round trip time we can only send these many bytes.
All right, so that's the idea of TCP's congestion control. Very much like what you guys did with guessing the price of these merchandises. Provided the feedback, loss or no loss. Loss, drop the rate. No loss, raise the rate. And in TCP, controlling the sending rate is equivalent of controlling the window size. So guys, if you still think that a go back N is fixed window size, all right, TCP being like go back N, unfortunately is not using a fixed window size. So another difference between go back N and TCP is that TCP uses its pipeline, all right, but the window size might change depending on the feedback coming back from the network. Okay, and guys, there's not going to be enough time to go down to the next mechanism how TCP controls the sending rate. So AIMD, okay, additive increase, multiplicative decrease, is the method used in the steady state. So when this TCP congestion is in the steady state. When TCP connection is starting in the initialization state, because TCP's congestion window always, the window size always start from a small number. And if we do additive increase, that's going to be too slow. So TCP in initialization implements this slow start mechanism to quickly ramp up the window size. Okay?
And it's very counterintuitive that they call this part of mechanism slow start. So slow start is in fact fast. And how fast? You will learn about it tomorrow morning. Okay, I'll see you tomorrow morning, and we'll continue to talk about TCP's condition control. And eventually you will see the finite state machine of TCP. Okay, not just the reliable data transfer part, but also mingled and mixed with the condition control mechanism. So you will see the full TCP finite state machine. And with that said, I say goodbye and congratulations again to Team 1 and Team 12. Okay, and all of you have passed quiz 27. Okay, I see you tomorrow. Bye. Okay, guys, bye. Interesting. Okay, bye. Okay, bye. Interesting. Okay, so I'm gonna end the stream now.